Today we begin our discussion of machine learning and related topics. Our objectives are as follows: define machine learning and understand basic machine learning principles, and introduce the concept of the data-driven approach and distinguish it from approaches that use explicit decision rules and handcrafted feature selection. So what is machine learning? There is no universally accepted definition, but a useful phrase by Andrew Ng that nicely summarizes the concept is the science of getting computers to learn without being explicitly programmed. Professor Tom Mitchell at Carnegie Mellon provides a more formal definition. A computer program is set to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with the experience E. We'll elaborate more on these definitions in a moment, but first, how are computers programmed to execute tasks of interest without machine learning? To make this concept more intuitive, let's use a brand new radiology resident as a substitute for our computer program. Our task is to program the resident to correctly identify whether a frontal chest radiograph is normal or abnormal. We give the resident a stack of images and an explicit rule that is followed the same way for each image. The resident will then label each image as normal or abnormal. The rule set may look something like this. 1. Look at the image. If ribs are present, go to step 2. Else, this is not a chest radiograph, and terminate the process. Step 2. Look at the right and left dark spaces enclosed by the surrounding ribs, diaphragm, and spine. If there's an asymmetric focus of high or low density, output abnormal. Or else, go to step 3. So on and so forth. Now you can imagine that one advantage of using this approach is that it does not directly depend on the amount of data we have. We've hard-coded a specific set of decision rules for the resident or computer to follow, and these same rules are executed whether we have a single chest radiograph or several thousand. However, imagine we now try to have the resident interpret a lateral projection, or perhaps an entirely new exam type such as an elbow radiograph. Our rule set is unlikely to generalize well to this new task, and at best will result in mediocre performance. So we see that for each new task or exam type, we would need to produce an entirely new set of decision rules based on hand-selected features that we know to be associated with the task of interest. Examples of such features could include asymmetric opacity, lucent lines indicating fractures, etc., depending on the task at hand. Well, what if we instead gave the resident a stack of images with the correct labels already assigned, and have the resident then attempt to learn the features that are most likely to result in a correct prediction for each image? Unlike hard-coded decision rules, once the resident has grasped the general process of learning the correct features, he or she may be given a new projection or completely new imaging study and use the same learning process to identify the best predictive features for the task at hand. You can imagine that, unlike explicit decision rules, however, the performance of the resident is going to depend strongly on the amount of data available. For example, if we only provide the poor resident a single radiograph and try to have them learn what features make it normal or abnormal, the task would be impossible. Given a stack of several thousand radiographs, though, the resident could much more confidently determine which features tend to be associated with each label. This is quite similar to how we will use data to teach our machine learning models. Fortunately for us, medical imaging data is becoming more and more ubiquitous, and the number of well-labeled datasets are increasing. With the availability of larger datasets, we'd like to leverage models that generalize well to different, though related imaging tasks or use cases. This mode of thinking is called the data-driven approach, and is summarized as follows. Collect a label training dataset, train a model using techniques that don't depend on explicit decision rules or features, then evaluate the model on similar, but new or previously unseen, test data. So the word model keeps coming up, but what exactly is a machine learning model? Simply put, a machine learning model is a mathematical function which takes as an input a data sample and outputs a prediction. Note that the symbol is read as y hat, indicating that it is a prediction by the model, not the true value. Depending on the problem of interest, this prediction may be a class label, such as disease or no disease, or an estimated value, such as the estimated blood pressure of a patient, given some input data about their lifestyle choices. However, unlike traditional mathematical model construction, we do not know what values to assign the parameters, aka weights and biases, of our model beforehand, and do not attempt to do so on our own. Instead, using the data-driven approach, we train our model on a set of pre-labeled data and allow the function to vary the values of its weights and biases until the output predictions most closely match the correctly labeled data. The total difference between our model's predictions and the ground truth data is the cumulative error, more commonly called the cost. The goal of training a machine learning model is minimizing this cost, a process known as optimization. Now recall Tom Mitchell's definition of machine learning. And let's see how it fits into what we just learned about training machine learning models. Let's drive this point home using our radiology resident. The resident's task T is to classify whether each chest radiograph in a stack of 100 is either normal or abnormal. In this case, we know the true label of each radiograph, normal or abnormal, and we'll measure the resident's performance P as follows. We'll take a tally of the radiographs the resident classifies incorrectly and call it the cost. For each incorrect classification, the cost increases by 1. The cost is then reviewed after the resident labels all of the images. The resident's goal is to minimize the cost. Initially, the resident does quite poorly, but is inspired to review the images for predictive features while comparing his or her answers to the true labels. Let's call this label review process the experience E. With some close scrutiny of the images, the resident begins to learn image features that best differentiate normal from abnormal. The resident then repeats the entire cycle hundreds of times, classifying the images, calculating the cost, and then studying again. If this undertaking is successful, we will see the resident's cost decrease with each iteration and performance P increase. Now let's turn this into a machine learning experiment. First, let's replace the resident with a model. This model will take each input image, perform a series of mathematical operations on the image data, and output a predicted label, normal or abnormal. Like the resident above, the model has no preconceived notion of what features are going to best differentiate normal from abnormal. That is, we have not explicitly programmed a procedure for it to follow. It will initially perform poorly, but like the resident, it will calculate the cost with each iteration and attempt to minimize its value by varying the parameters within the model. Through this iterative process, the model's predictions will more and more closely approximate the true values, and our model performance improves. We'll learn more about this process in greater depth later. In conclusion, we have defined machine learning and have gained a better understanding of basic machine learning principles. We've also introduced the concept of the data-driven approach and see how it differs from approaches that use explicit decision rules and handcrafted features.